Okay, let's get started. Any questions from last time on the data analysis? We put some Survey Monkey questions on the board. So if anybody has any issues with anything that we wrote, a lot of this is again going to be definitional. So I'm going to be basically words like trace, like pick, like gather, like shot, like source function. One of the things we didn't go over last time, which I'd like to go over very briefly. Actually, I'll get to that in a little bit. Let's just wait on that right now. So the one thing that we talked about last time was the travel time of events. How long does it take for the signal to propagate from the source to the receiver, right? And we basically just designated a velocity, a sound speed for the events. What I would like to do today is kind of just give you a little overview of how that sound speed depends upon the material properties of the medium. Okay? So one thing we can do to a solid is we can apply a pressure to the solid. We can basically squeeze it in all directions, right? And we know that if we apply a force to a spring by Hooke's law, that we get the force is proportional to the spring constant multiplied by the displacement of the spring. Well, the same equation occurs in solids, okay? This is basically fundamental elasticity. That is that if we apply a differential pressure, we get a volumetric strain. So pressure and strain are basically normalized force and displacement, Hooke's law. And they're related, in this case, by capital K, which is the bulk modulus of the material. Okay. And we have the same thing, relationship, if we apply a shear stress to a solid. We get a stress-strain relationship that looks like this, where the relationship between a shear stress and a shear strain is the shear modulus. Okay? So those are the two ways that we typically relate stress and strain. That's basically the equivalent of Hooke's law. And when we derive a wave equation for a solid, we use one of the big components is using Hooke's law. And I'm not going to go into the details of how we derive the wave equation, but I will go to this equation right here up at the top. So alpha is typically denoted as the p-wave velocity in a lot of geophysical literature. The wave velocity of the p-wave. And the critical equation is that second one. Don't worry about the first one for now. The second one is k plus 4/3 mu divided by rho, the square root. Beta is simply the square root of mu over rho. So let's look at some end members. What happens in a fluid? What's true about a fluid? By the way, mu is g in those previous equations. That's the shear modulus. So in a fluid, what do we have? Do we have any mu? Mu is 0, right? Mu is 0 for a fluid. So the shear velocity in a fluid is 0. The p-wave velocity is simply then dependent upon the bulk modulus. And all you get is a pressure wave. You can't get a shear wave in a Now, let's think about this a little bit more. If we think about F equals kx there, right? Let's say that K, the spring stiffness, is proportional to the shear velocity, all right? So let's think about this equation right here. And let's just replace, let's say this is proportional to beta squared, right? We won't worry about the density for now, but we'll say that the shear modulus, which is to say the spring stiffness of the material, is proportional to beta squared. So if I apply a force to a material, and I have a very, very low shear velocity, what happens to the displacement? Beta, if this is small, let's say I apply a constant force, right? So apply why don't you do this? Let's sit together and let me know what happens if I apply a constant force to a material with a small beta. What happens to X? It gets huge, right? So that's what happens in an earthquake, right? This is basically saying that if I have a very low shear velocity medium, I'm going to create a lot of shaking. Well, that's the wave equation. That's basically just simple elasticity. Whether it's linear or nonlinear, you get a lot of shaking where the shear velocity of the soil is low. And that's why we like to use surface waves to characterize the shear velocity of the soil, because we can actually tell where the shaking is going to be higher versus lower simply by the travel time of the shear wave. Okay. By the way, in ocean bottom sediments, in areas around the bay, there are transition zones. So you might have water, and then you get some kind of, not quite suspension zone, but a very, very low shear velocity, less than maybe 50 meters per second. And then you go into VS greater than 100 meters per second. So in water, there can be these suspension zones, and that's what can happen in large earthquakes, is that underwater you can actually have underwater slides and other things associated with this very, very shallow suspension zone. Fred, what have they measured like cores? Do you remember what how small the velocity, shear velocities are? They could be on the order of 6 or 7 meters per second. But about as fast as you can walk. So the sound wave, think about that. Actually the sound wave, you can create a sonic boom by walking in suspended zones. Kind of wild. Okay, so let's get back now to what we were talking about the last time, which is understanding wave events and the travel times associated with them. That's all I'm going to talk about in terms of velocity. The relationship between velocity and material properties is very complex. All kinds of things go into it, the matrix stiffness, the pore stiffness, the pore fluid, and we may get to that in a little bit later. But right now, just know that there's a relationship, that the spring constant essentially talks about the stiffness of the medium, and we may go in later on into the details of that, but not right now. Okay, so what we're going to do now is go into what happens if you have a heterogeneous medium. Okay, what if the medium is not one velocity? What happens to the waves or the wave fronts going from point A to point B? Or equivalently, what happens to the ray paths? And you've probably had this, if you've taken optics, you've probably seen a bunch of this before. Similar things happen in sound that happen in light. That is, that rays tend to refract off interfaces. You've all seen the example where you're looking down at the fish in the water, and if you look from an angle, it's actually at the wrong place. Everybody know that? Like if you think that the light wave is coming straight between the fish and you, you're wrong, because the light wave actually refracts at the water surface. And so if you put your hand down in the water, you won't grab the fish. Not good. Okay, so let's look at two examples here. I'm going to focus on this ray path to begin with. Okay, and notice in A, B, C,